Hello, my name is Vadim Yudintsev. I'd like to present a short investigation on a method of active debris removal using a spinning tethered system. Everyone is already familiar with the problem of space debris. The risk of in-orbit collision between existing debris or with active spacecraft is increasing. Therefore, the number of large objects like old spacecraft and upper stage rocket bodies in orbit should be reduced. Recently, many studies have been conducted to analyze debris removal methods such as robotic arms, foams, nets, tethers, and many more. Considering the high cost of developing a space system for active debris removal missions, it would be great if it's possible to use existing orbital stage like Fregat, Breeze as space tug in these missions. But many of the developed methods restrict the use of the existing orbital stage, requiring them to solve unusual rendezvous and docking tasks, or suppose using of space tug with non-conventional configuration. To use the existing orbital stage as space tug in ADR missions, all specific tasks could be delegated to an autonomous docking module. The space tug brings the ADM near the debris, ADM separates from the space tug and captures the debris object. Since we want to employ the existing orbital stage as space tugs, we only have to use a push towing scheme. So the module should go back home with captured debris. And the tether connecting the ADM with the space tug can simplify the docking process. And based on this method, we propose an alternative tethered towing scheme which does not require returning and docking of the ADM with the space tug. This scheme is suitable for any debris objects, even asymmetrical, and for any gripping device. The proposed solution is based on the rotation of the tethered system that induces centrifugal forces that strain the tether, allowing to apply tug thrust along the tether in the direction of the space debris object. The space tug applies its thrust periodically when the orientation of the tether relative to the orbital velocity vector of the system ensures the application of the impulse in the required direction. Applying the tug thrust along the tether could increase its oscillation amplitude, and the control system should damp the oscillation. In our previous work, we considered the use of tug thrust to damp tether oscillation, but that involves the space tug in solving the unusual tether control problem. Here we use another method. We can damp the tether oscillation controlling length of the tether. The tether free length is controlled by the reel, which is installed on the ADM adapter. The tether is coiled around the reel, and the rotation of the reel is controlled by an electric drive that provides the required torque. So in the rest of the presentation, we obtain the parameters of the control law for the tether reel that damps the oscillation of the tether. Here are the assumptions of our simple model. We consider the space tug and debris as point masses. We neglect the effect of Earth gravity to the tether rotation, and the tether is considered as massless spring. The motion of the system is considered relative to non-inertial frame, with the origin in the center of mass of the system. In the right side of the motion equations are the tether tension force, tug thrust, and two inertial forces caused by the acceleration of the center of mass of the system and the rotation of the tether. Here is the motion equations with the initial conditions. The equations has a stationary point for any constant tether free length. There is a stationary tether elongation, delta 0, and that elongation could be obtained from the following equation. This slide shows the Tether length control law we proposed. It depends on 3 parameters. And after determining the stationary solution, we can construct linearized equation of the motion in the neighborhood of the stationary point. This slide shows the resultant system of second order linear equation, and we can investigate the stability of the system depending on the control parameters. Applying Howitz criterion, we obtain the regions for the control parameters which ensure the stability of the system. If the parameters belongs to the stable region, the Tether oscillation are damped. Here are 2 regions, and the examples of stable and unstable solutions are shown on the left side of the slide. This slide shows a simple equation of the Tether real motion. We can express the torque that should be created by the electric drive to implement the obtained control law for the Tether free length. Let us consider a numerical example. Suppose that the tethered system has been formed consisting of the tug with a mass of 3 tons and a debris object with an autonomous docking module with total mass of 1.7 tons. The initial length of the tether is 2 kilometers and the initial angular velocity is 1.4 degrees per second. We consider 3 stages of the system motion, which are shown on the left side of the slide. This slide shows the graph of the tether length, its elongation, and the angular velocity of the tethered system. The graph illustrates the change in the length of the tether by the flight phases and the operation of a stabilizing control. The amplitude of the tether oscillation is decreased after the gripping and upon thrusters switching on and off. This slide shows the time history of the tug thrust. For the sake of clarity, only 2 pulses are shown. The slide also shows the torque created by the electric drive, the angular velocity of the reel, and the mechanical power of the electric drive. We can see that peak mechanical output is less than 4 kilowatts. Using these estimates, it's possible to select an electric drive and design a suitable power supply system for it. And in conclusion, rotating tethered system can be used to deorbit large debris object using space tug with conventional design. The space tug can be developed on the base of existing orbital stage or spacecraft. Presented model can be used to obtain parameters for the tether control law that dumps tether oscillation during the orbit process and to formulate requirements for the real electric drive. Thank you for your attention.